by now you've seen all of the main pieces of the recommender system algorithm, or the collaborative filtering algorithm. In this video, I want to just share one last implementational detail, namely mean normalization, which can sometimes just make the algorithm work a little bit better. To motivate the idea of mean normalization, let's consider an example of where there's a user that has not rated any movies. So in addition to our 4 users, Alice, Bob, Carol, and Dave, I've added a 5th user, Eve, who hasn't rated any movies. Let's see what our collaborative filtering algorithm will do on this user. Let's say that n is equal to 2, and so we're going to learn 2 features, and we're going to have to learn a parameter vector theta 5, which is going to be an R2. Remember, this is now vectors in Rn, not Rn plus 1. We're going to learn the parameter vector theta 5 for our user number 5, Eve. So if we look in the first term in this optimization objective, well, the user Eve hasn't rated any movies, and so there are no movies. There are no movies for which Rij is equal to 1 for the user Eve, and so this first term plays no role at all in determining theta 5 because there are no movies that Eve has rated. And so the only term that affects theta 5 is this term. And so we're saying that we want to choose vector theta 5 so that the last regularization term is as small as possible. In other words, we want to minimize this lambda over 2 theta 5 subscript 1 squared plus theta 5 subscript 2 squared. So that's the component of the regularization term that corresponds to user 5. And of course, if your goal is to minimize this term, then what you're going to end up with is just theta 5 equals 0, 0, because the regularization term is encouraging us to set parameters close to 0, and if there is no data to try to pull the parameters away from 0, because this first term it doesn't affect theta 5, we just end up with theta 5 equals the vector of all zeros. And so when we go to predict how user 5 will rate any movie, we have that theta 5 transpose xi for any I, that's just going to be equal to 0, right? So because theta 5 is 0, for any value of x, this inner product is going to be equal to 0. And what we're going to have, therefore, is that we're going to predict that Eve is going to rate every single movie with 0 stars. But this doesn't seem very useful, does it? I mean, if you look at the different movies, Love at Last, this first movie, a couple people rated it 5 stars, and for even the Swords versus Karate, someone rated it 5 stars. So some people do like some movies. It seems kind of not useful to just predict that Eve is going to rate everything 0 stars. And in fact, if we're predicting that Eve is going to rate everything 0 stars, we also don't have any good way of recommending any movies to her, because all of these movies are getting exactly the same predicted rating for Eve, so there's no one movie with a higher predicted rating that we could recommend to her. So that's not very good. The idea of mean normalization will let us fix this problem. So here's how it works. As before, let me group all of my movie ratings into this matrix Y. So just take all of these ratings and group them into this matrix Y. And this column over here of all question marks corresponds to Eve's not having rated any movies. Now, to perform mean normalization, what I'm going to do is compute the average rating that each movie obtained. And I'm going to store that in a vector that we call mu. So the first movie got 2 5-star and 2 0-star ratings, so the average of that is a 2.5 star rating. The second movie had an average of 2.5 star, and so on. Then the final movie had 0050, and the average of 0050, that averages out to an average of 1.25 rating. And then what I'm going to do is look at all the movie ratings, and I'm going to subtract off the mean rating. So this first element 5, I'm going to subtract off a 2.5, and that gives me a 2.5. And the second element 5, subtract off a 2.5, get a 2.5. And then these 0 zeros, subtract off 2.5, and we get minus 2.5, minus 2.5. In other words, what I'm going to do is take my matrix of movie ratings, take this Y matrix, and subtract from each row the average rating for that movie. So what I'm doing is I'm just normalizing each movie to have an average rating of 0. And so just one last example, if you look at this last row, the 0050, I'm going to subtract 1.25, and so I end up with these values over here. Okay, so now, and of course the question marks stay a question mark. And so each movie in this new matrix Y has an average rating of 0. What I'm going to do then is take this set of ratings and use it with my collaborative filtering algorithm. So I'm going to pretend that this was the data that I had gotten from my users. I'm going to pretend that these were the actual ratings I had gotten from the users, and I'm going to use this as my data set with which to learn my parameters theta j and my features xi from these mean normalized movie ratings. When I want to make predictions of movie ratings, what I'm going to do is the following. For a user j on movie I, I'm going to predict theta j transpose xi, where x and theta are the parameters I've learned from this mean normalized data set. But because on the data set I had subtracted off the means, in order to make a prediction on movie I, I'm going to need to add back in the mean, and so I'm going to add back in mu I. And so that's going to be my prediction, where in my training data I subtracted off all the means, and so when I make predictions I need to add back in these means mu I for movie I. And so specifically for user 5, which is Eve, the same argument as the previous slide still applies, in the sense that Eve had not rated any movies, and so the learned parameter for user 5 is still going to be equal to 0, 0. So what we're going to get then is that on a particular movie I, we're going to predict for Eve theta 5 transpose xi plus add back in mu I. And so this first component is going to be equal to 0 if theta 5 is equal to 0. And so on movie I, we're going to end up predicting mu I. And this actually makes sense. It means that on movie 1, we're going to predict Eve rates at 2.5. On movie 2, we're going to predict Eve rates at 2.5. On movie 3, we're going to predict Eve rates at 2, and so on. And this actually makes sense because it says that if Eve hasn't rated any movies, we just don't know anything about this new user Eve, what we're going to do is just predict for each of the movies whatever the average rating that those movies got. Finally, as an aside, in this video we talked about mean normalization, where we normalize each row of the matrix Y to have mean 0. In case you have some movies with no rating, so this is analogous to a user who hasn't rated anything, but in case you have some movies with no ratings, you can also play with versions of the algorithm where you normalize the different columns to have mean 0 instead of normalizing the rows to have mean 0, although that's maybe less important because if you really have a movie with no ratings, maybe you just shouldn't recommend that movie to anyone anyway. And so taking care of the case of a user who hasn't rated anything might be more important than taking care of the case of a movie that hasn't gotten a single rating. So to summarize, that's how you can do mean normalization as a sort of pre-processing step for collaborative filtering. Depending on your data set, this might sometimes make your implementation work just a little bit better.